So good morning, good afternoon, good evening, everyone. Thank you for being here today, people in person here, University of Queensland, in the beautiful St. Lucia campus, and people online. And first of all, I would like to thank particularly Josh for inviting me today to organize also this event after the World Conference on Timber Engineering. And I have the pleasure today here to be with some of their young researchers and PhD students here at the University of Queensland. And I've been trying to put together like a talk about some of the topics and aspects that have been looking specifically to structural fire behavior, particularly to structural timber we're going to discuss today. And I've been focusing on a topic that is becoming more and more into the research, but also the discussions in practice related to actually what happens after flashover, but not only the fully developed phase of the fire, but also the fire decay and cooling. So today, regarding the general overview, what I'm going to talk about is I would like to give you a bit of overview of the fire safety strategy and timber structures. So I'll discuss first related to fire decay and the cooling phase. Then also I'm going to try to put this aspect related to timber structures. Particularly, I'll show you something related to a numerical modeling study that I did and also presented on Wednesday during the World Conference on Timber Engineering. I'm going to give you a bit of insights of a very recent experimental research related to a topic that I've been doing over the last 6 months with an MFSC student. Then I'll try to put into the mass timber structure context some concluding remarks, and then I'll be happy to take any question, both online and in person here. So when we try to put the whole story of structural fire engineering in the context, the idea is that when you're trying to develop a fire safety strategy, usually we have two clear objectives. First objective is life safety. The second objective, that is sometimes not always the main objective of the fire safety strategy, but also is property protection. Then it can be also extended to resilience. So in terms trying to create an infrastructure, then in the case of fire, it will still respond well to the event and also would go back to operation in a very short manner. So we usually decide and we put together a bunch of different fire safety measures because we would like to achieve our objectives, and we can mainly focus on detection, alarm, evacuation, smoke and heat management, compartmentation, suppression, fire service intervention. But in general, what I wanted to discuss today is that mainly at the bottom of everything, we have structural integrity. So as soon as, for example, here in the picture, we have a high-rise building, you can put together everything in terms of fire safety measure, but if you don't ensure that you have a structure that actually brings its own objective, so carry the load and stay in place during the fire event, it doesn't matter to actually put all the measures because we want to actually achieve the objectives. So today I'm going to discuss about structural integrity, so structural fire engineering, and try how we can try to achieve these goals, particularly related to timber structure. So the first point is I'm just going to go quickly through some basics of designing fire-safe timber structures and try to bring together, fire decay, cooling, and then going towards some experimental research and medical modeling. So what we know, and I guess here I'm going to go quite quickly, but when timber is exposed to elevated temperature, to fire in general, to elevated temperature, we have different types of thermal decomposition processes that would affect the material, decompose it, and therefore going to go and affect the structural performance of the structure itself. So what we have is a first moisture migration, evaporation. The wood will possibly achieve a specific temperature depending on the species, will go possibly beyond 200 degrees, decompose, release combustible gases, but in the end, the outcome of this is that we're going to have a char layer, we have a charred timber that for our structural purposes has no strength or stiffness. So we have to start thinking about how actually the cross-section is affected by fire and how we can calculate the load-bearing capacity of possibly this element. Well, you see here on the slide, you see a wall with the fire exposed from one side. What we can do is that at any time of the fire exposure, we can try to define the thermal gradient through this element, and we can divide timber in different regions. So charred timber, heated timber, dry timber, and virgin timber. And then what is the typical way that we solve it? We try to get the effective cross-section of this element by taking the initial cross-section, removing a part of the timber that are actually charred, and removing a part that are actually of the timber that takes into account of the timber that is not fully charred but is heated, so has lower mechanical properties. Well, we see this method is a classic method that we see more or less in every code around the world. Here there is a European standard, there is an American one, Australian and New Zealand one, but the same concept, we have possibly different values and different details about that, but the whole concept of designing timber structure in fire condition is something that is quite common all around the world. So what we usually do, we focus on the different parts. The first one is we focus on char depth. So they consider the contribution of char wood, so non-strength and stiffness, and we typically assume as the temperature of charring are something around 300 degrees, which is a quite rough assumption, but this is quite well established in the field. We can discuss about how well conservative or not conservative it is, but this is something we can go also later into the details of that. What we do, we usually take like a specific duration of the fire, fully developed phase of the fire. We, according to the common approach of following standard fire resistant tests, there is a common belief. We usually assume that this is constant. We can discuss about this for a long time, but this is a strong simplification. But all of it goes into discussion is that how well we predict and also how well we are conservative in predicting this value. Because in the end, we are trying to design, and then as a classic civil engineering approach, we want to make sure that the structure actually remains in place, keeps its integrity and its stability. Then we have the other aspect, which is the so-called zero-strength layer, which is considered uncharred wood, but that has been heated above ambient temperature. We have different values of this. So the previous zero-strength layer, according to Eurocode 5, and would assume 7 millimeters. That would increase from 0 to 7 millimeters within the first 20 minutes of the fire exposure. And then a new version of Eurocode 5, we have mainly a value that, depending on mechanical action, fire protection, fire resistance rating, this value would move from 7 to 16 millimeters. But in general, what we do is that once we define an appropriate fire scenario, and we can discuss this now in a second, what is an appropriate fire scenario, then we can just take an element and we can start looking at how the different isotherms, the different, let's call it the thermal decomposition processes would penetrate within the load-bearing structure. And then we define, again, char layer, zero-strength layer, and the effective cross-section. So what we usually do is that the common approach is that if we take what we call it natural fire, so a fire that is composed of different phases, we start from ignition, then from ignition we have a growth phase. If the condition are such, we would possibly achieve flashover, where all the fuel within the compartment will burn and would contribute to the fire. Then we have a phase of fully developed fire, and then follows the fire decay and cooling phase. What we typically do, we take a representation depending on the standard, depending on the condition that would link to mainly the fully developed phase of the fire, because we acknowledge with time that the fully developed phase of the fire for structural fire engineering is that the heat fluxes and the temperature, the heat fluxes that would possibly challenge the structure through the heat insult. And therefore, we focus mainly on that part, and we focus particularly, we specifically test for a specific duration. So what we do, this is, for example, a test in our laboratory in Slovenia at ZAG. You see here a loaded CLT slab that after the end of the test, the furnace is actually opened. The fire is still going on the exposed surface of the CLT slab. But then what we do, as soon as we test it for a certain amount of time, then we stop the test and then we remove the sample because we actually want to assess the exact condition at the end of the test. So what we do, if the sample fails during the actual duration, that is the fire or the definition of the fire itself, then this is a problem. If actually the element survives and carries the load and does the job during the specific duration, we are happy with that. But then, what you see immediately here in the slide is that there is something happening during at the end of the fully developed phase of the fire. There is a fire decay phase, there is a cooling phase. Then I'm going to give you now some details about the process, the physics itself. But what does it happen here? So first, I'm going to go through the fire dynamic aspects of these phases, because this is something that what we realized is that 2 years ago, I was discussing with different collaborators And we start seeing that these topics, so if you just put on any search engine for scientific publication, if you put fire, decay, cooling, structure, concrete, steel, wood, anything related to structural engineering and main construction material, you see there are more and more papers that are published related to this topic, either with that keywords in the abstract or in the titles itself. You see the general, all the abstracts, so all the journals and fire journals, and on the right you see the main three fire journals. You see more and more this topic discussed and published. So what we decided is 2 years ago with Professor Torero at the International Symposium for Safety Science, we decided to sit down and try to bring together some ideas related to these phases, because we realized that it's possible there is a lot of discussion around these topics, but often fire, decay, and cooling are mixed up or not well defined, because traditionally they were not the key focus of the analysis, because we've been always focusing on the fully developed phase of the fire, high temperature, high fluxes. So whatever was happening afterwards was of a secondary importance. So this is why is this important, because when you have a sort of, when you have a load-bearing structure, when you have an element, for example, here you see a compartment with walls and an opening, then you see an element, here I put for simplicity a steel beam that would follow the temperature Ts, and then we have a temperature of the gases Tg, followed by fire. What we usually assume, for example, taking Eurocode 1, we usually define the heat flux, the net heat flux towards the structure as a function of convective transfer and radiativity transfer. But what you see is that in most of the equations, we define the sort of, we call it the radiation temperature, the convection temperature, that are assumed as the same one, because mainly during the fully developed phase of the fire, you have a very thick, very dense, optically thick smoke. So mainly both the convection term and the radiative term of this equation that will contribute to heat flux is directly related to the gas, so the smoke layer. But then when you start having different conditions in the compartment itself and you try to generalize this, particularly both for the growth phase, but also then also becomes relevant for the fire, decay, and the cooling phase, then if you're trying to generalize it, you see on the left the convective term. So you would have to discuss about which gas temperature you actually have to consider. But then if you want to discuss about radiation heat transfer, you have to start thinking, if you don't have any more optically thick environment, so you don't have a very black smoke that radiates heat at a very high rate, then you start having a sort of either a transparent environment or a smoke layer which is not so dense. Then you start thinking which elements, which radiation bodies and radiation surfaces are actually my element exchanging heat with. And here you see I put generally as a sum of all the possible elements that would be in the compartment, plus, of course, we can put in generally into a heat flux coming from the flame. But then also the flame can be considered as a radiation surface that would exchange possibly heat with the element itself. So if we take it generally, I'm going to try to go through the different, just going to remove this. I'm just going to go through the different phases of the fire. So I'm going to try to discuss about what happens in the different phases, what we expect, and what possibly will be relevant for our structural calculations. So when we achieve ignition, what we see, and we start looking at the heat release rate of the fire, we typically assume a quadratic evolution of the increase of fire. And then so you see a curves like this. And then what you typically see is that if this is the gas temperature, typically the gas temperature follows somehow the evolution of the heat release rate as well. What you see then, if I try to, so this is the curve of the net heat flux, and then this is the two curves that would represent the evolution of the linings and the structure surface. So what you see here, for example, you see in this picture, you see here I made an assumption that the actual thermal inertia of the structure is much higher than the thermal inertia of the linings, which is much, much higher than the thermal inertia of the gases. In a way that you mean that the material with the highest thermal inertia has a more inertia responding what actually happened in its environment. So here you see that the gases, they increase much faster than the linings. So the surface of the linings in the compartment are a bit delayed, and the structure, since it's here you have a steel section, but it could be a concrete slab or a concrete beam, has a higher inertia, so it takes a longer time to follow what actually happens in the gas phase. But what we usually assume for structural fire calculations is that we really usually neglect the growth phase, because we see, unless we have a very big compartment, we have a big collection of smoke that before transition to flashover, we don't consider this phase because the heat fluxes and the temperature are relatively low. When becomes relevant is that when we achieve, if the conditions are such, we achieve flashover. So in flashover, what we have, depending on the fire and the condition of the compartment, you can have a fuel controlled or a ventilation controlled heat release rate of the fire, but in general, the fire goes in a sort of steady state condition. It's a static condition that defines of heat release rate. And then the compartment goes also in thermal equilibrium. So you start balancing what is actually brought into the fire. You start balancing what are the losses at the compartment walls, the losses at the compartment opening. But in general, you tend to a sort of almost steady state temperature, steady state heat release rate, and steady state temperature in the gas layer. What you see is that, of course, you have a peak in the heat flux when actually there's the greatest difference between the gases, let's say, and the temperature of the structure itself. But then at a certain point, the heat flux tends to, again, to a steady state condition, to a specific value. What you see, again, the heat fluxes would lead here, I'm just focusing on the surface temperature, but again, the linings would follow what happens in the gases, and the structure would follow, again, what happens in the environment itself. Then now, before going there, and then if we discuss about heat transfer in the compartment itself, then what I mentioned earlier, in the fully developed phase of the fire, the characteristic is that we have a very thick thermally, so the smoke is very dense, very black. So what you have is mainly any structure that is, for example, exposed on the ceiling, like in this case. The main heat transfer and main heat transfer goes from the smoke layer. So both convecting term and the radiative term is exchange of the smoke layer with the structure itself. Then when you start having a fire decay, so the fire decay means that at some point, since the fuel load in the compartment is somehow defined, at a certain point, you start having fuel depletion. So the fuel depletion, what I here assume as, again, as a quadratic decay, but in general, what you see is that the fuel is not anymore enough to feed the heat release rate during the fully developed phase of the fire, so you start having a decay in the fuel itself. And similarly to what we've seen in the growth phase, then we can expect that the gases in the compartment will also follow the decay of the fire itself. Then what happens is, since both the linings and the structure higher thermal inertia of the gases, even if the gases are cooling down, the higher inertia of the structure would actually, or the linings, would take a longer time to cool down. And this is simple, thermal inertia and heat transfer calculations. What you see is that at a certain point during the fire decay, here made assumption because it's an illustrative case, you start having still, so when the temperature of the gases are still higher than the temperature of the linings of the structure, you still have a positive heat flux, because mainly you still have a heat flux that actually get into the structure. And then a certain point when actually the temperature of the gas or the heat flux coming from the flames and everything goes below a certain threshold, the heat flux becomes negative, because what mainly you have is the element somehow start having a negative flux. So you start taking heat from the mass of the element itself and releasing into the compartment or the gases or through radiation. So if you're trying to generalize now this equation, you see here now in terms of the convective term, you have the gases again, you have like a convective term, and you have the structure that actually exchange energy with the gases. And you can imagine as soon as the temperature of the structure is higher than the temperature of the gases, this heat flux becomes negative, or this contribution of heat flux becomes negative. Radiation, we go back to what I mentioned earlier, the generalized expression of this equation, then depends. Depending on the lining you have, if you have a very thick concrete wall, or for example, a shear wall that has been absorbing a lot of heat, and it's going to take a long time to actually cool down, will also radiate heat from its surfaces to the structure itself. And then finally, I consider here the radiation from the flames. This has to be, you have to take into account case by case, but you can also, as soon as the environment becomes less dense, less opaque, then you start having an influence of that. What happens during the cooling phase is that the cooling phase, since you have no more fire, you have no more heat release rate coming from the fire itself, we can expect, if the compartment is small enough and the opening is big enough, the gases, they quickly go into ambient conditions because the mix at the compartment opening is quite big. Therefore, the temperature or the gas temperature in the compartment actually gets very ambient very quickly. What happens again, depending on the inertia of the linings, depending on the inertia of the structure of the linings will take time to cool down depending on their thermal characteristics. And what you see, the heat flux is negative, but at a certain point goes back to thermal equilibrium until it goes to zero. But what you see here again, if you're trying to do the quantification of the heat flux to the structure, then in terms of the convective term, now the actual temperature of the gases is ambient. So this is definitely a negative term, so it's cooling, because the temperature of the structure due to the higher thermal inertia is higher than the temperature of the gases, which is ambient temperature. And then again, the radiative term depends on what the structure is actually seeing. So this is a bit how I try to explain, how we try to put together all these aspects of what actually happened during the various phases. But this defines clearly a difference between the fire decay and the cooling phase. Because the fire decay is the cooling phase, again, it depends. The fire decay, you assume as a fire. So there is still some sort of level heat release rate in the compartment. What happens instead in the cooling, again, to me, I try to refer particularly in this definition into the cooling of the compartment as overall energy within the compartment. But then if we discuss about cooling of the structure, the actual cooling of the structure starts here, when you start having a negative heat flux at the compartment, at the structure itself. So if we discuss about cooling of the compartment is something, but if you discuss about cooling of the structure, then you have to start looking at the energy balance of the structure you actually study. So now, discuss about these phases. I'm going to discuss why we're here today discussing about these phases and timber structures. Why should we care? So what we see here is that when wood, connected to what I discussed earlier, when wood is exposed to fire, you start having a gradient through the wood, and then this gradient would, of course, get deeper if you have a longer duration of the fully developed phase of the fire itself. What happens is that when the fire dies, you're going to the fire decay, the cooling phase, you start having a cooling closer to the surface, but then you start having redistribution of energy and heat through the thickness of the timber itself. And this is important because what we discuss always related to timber structures, and that we always have this char layer that protects, or as a lower thermal conductivity, the timber itself. So the char layer, somehow, if we manage to keep it there, is protecting the virgin wood that is actually sits underneath. But this problem, when you start looking at the cooling phase and the fire decay, the problem is opposite. So as the wood is protected by the char during the fully developed phase, when there is actually heat and salt, then when the wood is trying to cool down, actually happens the opposite. Because now the wood is an insulative material, char is insulating. So if you have a cooling at the surface, then you start having a lot of heat inside, and the char is actually protecting for that piece of wood to actually cool down. And one point that I wanted to mention here, I'm showing you a sort of wall. So you have a one side exposure from the fire, and then you have a heat and salt through the thickness itself. Of course, for a wall, heat can penetrate through the wall itself, but then possibly the heat then reaches the unexposed side of the fire, then you start having losses from that side. But then this problem is much more critical for column, for example, because in a column, you start having heat flux coming from the surface, but then at a certain point, no problem. But then at a certain point, what you start having, depending on the size of the column, you may get collection of heat actually in the core of the column, because actually heat doesn't have the chance to go anywhere else. Why is relevant this for timber structures? Because as we discussed, we usually assume 300 degrees as the char, the temperature for wood to char. But then this means that between ambient temperature and 300, we have a big drop in the mechanical properties of wood. And this is particularly relevant because usually if we compare to other materials, they possibly would expect and would experience the same behavior, then you see that for wood, this drop of mechanical properties is much sharper. Compared to other materials like concrete and steel, they would possibly experience the same concepts, because when you have concrete or you're trying to protect the tensile reinforcement in concrete, you still have the same problem, and the same problem applies to a protected steel section. Then when you're trying to protect during the fully developed phase of the fire, but when it's cooling down, actually that cooling is prevented by the fact that you have insulation. So, but in wood, in timber, this is more relevant because the actual temperature that are relevant for this problem are much lower, and therefore we may experience a bigger problem. So what we do is that compared to what we discussed earlier, if you take, for example, the fire energy and the natural fire that I showed you earlier, what we can start seeing is that the effective char depth in the timber structure, you start having not much during the growth phase, during the fully developed phase increases, but then you still have a contribution of the char depth during the full decay and the fire decay and the cooling phases. And if we look at, for example, the load-bearing capacity, which is a function, of course, of the effective char depth and therefore the effective cross-section, then if we discussed earlier about the difference between assessing the timber structure between at the end of the fully developed phase or at the end of the fire decay phase, you can see here there may be a bit difference between these two. And this is something that, for example, in a lot of studies have been done on this topic. Some studies have been done over the last few years. This is, for example, the case of tests that have been done in a consortium between different countries. These are a timber column that it was testing in a furnace. And what you see was tested for 15 minutes and then it left cool down in a furnace by itself. And this is what happened after 153 minutes. So actually the column failed almost 2 hours later than the actual end of the fire test. And what you see here, for example, these temperatures are not from this test, but what you see is that you have in this specific case, you have the temperature of the furnace. This was 1 hour standard temperature sum curve, and then you see the temperature in depth in the timber. What you see is that the temperature close to the surface, which is the highest during the fully developed phase, then it drops fast during when you turn off the furnace. And then what you can start see is that the gradient you have at the beginning, so you have the blue, orange, and gray, then at a certain point, the orange goes above the blue. So this means that the temperature of the surface, which was the highest during the fully developed phase of the fire, then it cools down faster, while the temperature more in depth, they were more protected during the fully developed phase of the fire, now becomes higher than the one close to the surface. And this is also another fire test that they did in France at Cerib. There you see that the fully developed phase of the fire, this is like a logarithm scale, and I found this online, but you see that this is the gradient during the test, and then you see that still temperature penetrates inside wood. These are the gradient through the wood during the experiment itself. So this is a bit of the problem, and this is something that, okay, I gave like a big overall introduction, but I wanted to try to bring a bit onto the problem, why we're discussing today, why we are here today. And now we're gonna try to bring you to some of the outcomes we found with me and some collaborators related to numerical modeling, but also some experimental research. So the numerical modeling and the study that I did, that I also presented during the World Conference on Timber Engineering, what we did, we start looking at this problem numerically. So if we take a timber wall, a semi-infinite solid with the specific timber properties, so 420 kilos per cubic meters for the density and a moisture content of 12%, which is quite typical, we assume Eurocode 5 thermal physical properties. We define a boundary condition on the surface, and we start looking, if we put together a heat transfer model, how actually the gradient and the energy distributes through the wood during specific fire conditions. So if we go back to the previous concept of trying to take a wall, a slab, a semi-infinite solid, and to define how the different parts of char, zero-stem flare, or heated part of the wood and effective char depth evolve over time, you can start seeing this is an example. So what you see here on the left is a temperature axis, and on the right is how actually the different depths, and I'm going to discuss about these points, actually evolve in time. So regarding the temperature, this is, for example, is a parametric fire curve. Parametric fire curve is a model that is also available on Eurocode, where you actually define the fire conditions as a combination of the heating phase and the cooling phase. Heating phase is representative of the fully developed phase of the fire. The cooling phase is not well defined. I tried to dig into the characterization and how this was actually obtained, but it's a mix of fire decay and cooling. But in the end, what you see is that you have a fully developed phase that has a typical logarithmic behavior, and then you have a linear cooling, which of course brings a lot of assumptions. Particularly this problem that I'll show you now is we define a specific curve that will bring to 60 minutes of standard fire curve and then followed by about 2 hours parametric fire cooling. So if we focus to the char, the evolution of the evolution of the char depth in time, what you see here, you see that the char at the beginning is start increasing during the fully developed phase of the fire, but is still penetrating for about 20 minutes, also during the cooling phase, because actually you see the temperature are still very high in the compartment itself. So you start still having a contribution of the char during the cooling phase as well. If we discuss instead of zero-stem flare, so I'm going to tell you quickly how we actually estimate. We follow different approaches, but you see that the zero-stem flare, so the part of wood that is actually heated, is relatively low during the heating phase, but then this value keep increasing during the cooling phase because, as I discussed earlier, there is a distribution of energy within the timber element, and therefore this value actually increases. And what is relevant to me is that in the end, the two values are comparable. We discussed about between 30 and 38 for this specific problem. But then if you try to put together the two of them, trying to quantify the effective char depth, then you see that actually most critical condition is actually achieved almost close to the end of cooling. So you have to consider the whole scenario to actually properly assess the structure itself. So what we did, we started taking this concept, so the Eurocode parametric fire curves, and we completely parameterized this problem in a way that you can see that you stack it, because what we realized is that if you take the parametric fire curve problems and if you look into the equation of that, the actual problem is a 2 degree of freedom problem. So you have from one side, you have some contribution of the ventilation, so the opening factor, and from the other side, you have the fuel load density that also defines, how much you're familiar, but opening factor defines also the gamma factor, which is also a function of the thermal inertia of the linings, so a lot of aspects. But in general, if you parameterize this problem and you start looking at how the different fire condition will be affected by the different factors, so if you look at the maximum temperature in the compartment itself, what you see that the opening the highest, so you have the two cases, so you have ventilation control fires and fuel control fires. In the case of ventilation control fire, you usually achieve the highest temperatures, and actually you get the highest temperature in the top right of this plot, where you have the highest fuel load densities and the highest ventilations. Then we can discuss also about the cooling rate. You see that the cooling rates are much lower for small openings. And also here in the bottom of the slide, what I showed the different durations of the different phases. So the heating phase duration, the cooling phase duration, and the total duration of the fire scenario itself. What I wanted to highlight, apart from discussing about values, what you see here is that the longest fire durations, both for the heating phase and the cooling phase, you get it to the top left of this plot. So very high fuel load density and very low opening factors. Wanted to highlight this because this is going to have an influence on the result itself. So if you start looking at our timber element and how the different parts of a contribution of the char depth and effective char depth would behave in time, what you see here is that in the D char, so the thickness of the char, which was assumed as the penetration of the 300 degrees isotherm, you see here on the plot the contribution of the heating phase, the cooling phase, and the total char depth. What is important that I wanted to highlight, you see for the cooling phase, we have values between 0 and 10. So we don't have a much contribution of the char depth during the cooling phase, while most of the contribution to the char depth is actually due to the heating phase when we have high temperatures. And what you see here, we have more or less a ratio between 0 and 10 and 10 to 70. So the value is much higher. And then you get to total char depth in this ratio. Then if we start looking instead of the heated timber, so the zero strength layer, so here we we look at the problem from the thermal side. So here we assumed, and we saw in the literature that usually people associate that the zero strength layer can be associated, can go as low to 80 degrees, 120 degrees. And depending on the conditions of the element itself, can go as low as 80 degrees. So if you take the 80 degrees scenario, so this means mainly instead of tracking now the 300 degrees isotherm, now I'm tracking the 80 degrees or the 120 degrees isotherm, and then I'm removing the char depth, so the part that is actually considered char. You see here that depending on the conditions, of course, if you get a lower temperature, you get higher values because you get a thicker slice of the wood itself. But you see that now what is relevant to me, apart from the value itself, the values between the heating phase and the cooling phase are comparable. So here you see for the case of 80 degrees 300, 0 to 40. And here you get up to 60, 70. And then in the 120 case, you can see here 20, 20. So the values are actually very comparable if you look at the part of the heated timber during the heating phase and the cooling phase. So this was carried a big assumption of the fact that we didn't look at, so zero strength layer is a structural concept because it's trying to take into account the heated timber and the reduction of mechanical properties of timber in order to see how this contribution of the heated part will actually have to be removed to consider the effective cross-section. So what we did as well, we took at any point the gradient through timber itself, and we tried to define in 3 different zones: the char, heated wood, and cold wood. So here, what we see, I discussed earlier, the part that was above 300 degrees was considered char depth. And then now is that how do we define what we did earlier is that in order to take the thickness of the zero strength layer, we took another line here at 80 and then in 20, and we took the thickness that will go from 300 to 80 or 120. But also we look at that from the mechanical point of view. So from the gradient, taking the plot that I showed you earlier regarding the reduction of mechanical properties of wood, depending on the action, compression and tension, here I just show you a curve which is representative, you can find mainly the reduction of mechanical properties as a function of depth. So from the gradient, then you get the reduction of the mechanical properties. Then if you're trying to understand, you start trying to see how you can balance the distribution over the thickness compared to having a binary problem. So having having zero strength layer as zero load bearing capacity and wood that is below the zero strength layer, which actually has the maximum, the ambient load bearing capacity, then at that point you can quantify the zero strength layer. So if we take the reduction of mechanical properties for compression and tension, what we figured out first is that the values for compression are comparable to the 80 degrees ones. And again, you see here that the values during the heating phase, the cooling phase are actually comparable. If you take the tension cases itself, what you see would experience a lower reduction of mechanical properties in tension at elevated temperature. You see lower values, but again, comparable values during the heating phase and the cooling phase. And then if you try to combine the two cases, then you're trying to see what is the actual temperature where you draw the zero strength layer in compression and tension for all the different cases. We actually found it quite surprisingly, quite interesting, the fact that if you look at the element in tension, then your zero strength layer goes from 300 to about 110, 115 degrees. And if you take in compression, it goes as low as 65, 72 degrees. So this is quite well, we are surprised, but at the same time, we shouldn't be surprised because the thermal properties of wood are quite well defined. So the gradient we actually will get through the wood is is well defined in a way that if you take the reduction of mechanical properties, you actually can quantify the zero-strength layer. And if you put all the results together, you try to put together both the contribution of the char, the contribution of the char, the zero-strength layer, so summing both zero-strength layer and char, you can see for the case of 8400, 120, and 300, you can see that the actual maximum values, as we have seen so far, are always in the top left corner. Top left corner, if you remember from the previous slide, when I show you the evolution of the fire condition as a function of opening factor and fuel density, you see that in the top left corner were actually the longest fire durations, while the highest temperatures in the compartment were achieved in the top right corner. So this means that what mainly drives the problem, since it's a transient problem, is not much about the actual temperature is achieved within the compartment, if you achieve 900 or 1000 or 1200 degrees, but actually since it's a transient problem that evolves in time, what drives the problem is the actual fire duration. And then this was the main outcome that we found out from studying the problem numerically. Then we took these results and we started looking, okay, how can we study this experimentally in a way that we can clearly control carefully what actually happens through a wooden element exposed to somehow a fully developed phase of the fire and then also fire decay and cooling. So what we did, we took a piece of timber, 200 by 200, 120 millimeter thick, three lamelle, each lamella 40 millimeters. We applied thermocouples at different depths from the side, also following what Ian has been telling us about thermocouple accuracy in particularly low conductivity material, low thermal inertia materials. And we have been started looking at how the evolution of the temperature and the evolution of the different isotherms in time. So here I show you a case of, we have a radiant panel, we have here the timber sample, you see here the surface of the timber sample, and I'm showing you here the evolution of the gradients, here on the right of the plot, and on the left, the evolution of the different isotherms, the 300, 250, 200, 150. This specific case that I'm showing you is a 20 minutes fully developed phase of the fire, which is, in this case, we defined the fully developed phase of the fire, we applied 50 kilowatts per square meter. And then we have, during the cooling phase, during the fire decay phase, what we did, we decreased linearly the heat flux from 50 to 0. So what you see here from the test, you see the time on the top, where you see that at the beginning we have a fixed heat flux for a specific duration, that it was 20 minutes. And here I didn't have the time to give to make an interactive plot that would show you the gradient through the element, but you see that, of course, during the fully developed phase of the fire, you start having an increase in the gradient itself. Then what we start doing, we start removing the panel away. Removing the panel away, therefore, we start reducing the heat flux. Reducing the heat flux that would somehow, in a simplified manner, decrease linearly, and then we start looking at what's actually happening through the sample itself. So it was 20 minutes fully developed phase, 50 kilowatts, 20 minutes that we decreased linearly, the heat flux, and then we left it to cooling phase. So it was natural cooling. Let's see what's actually happening during in the sample itself. So we did two cases. So the first case, we look at natural cooling. So we just add a heating phase of different durations, 20, 30, and 40 minutes. And you see here the cases, 20, 30, and 40 minutes. In this case, we have 20 minutes, 30 minutes, and 40 minutes of, let's call it, fully developed phase, followed by natural cooling. What you see here, what is interesting, and these are average curves, what you see is that as soon as you stop the fully developed phase of the fire, what happens, these isotherms, this is the specific 300 degrees isotherm, plateaus. So there is no actual penetration in these experiments as we did. There is no much penetration of heat during the natural cooling itself. And what you see here is that if you take these curves and you do a derivative of that, so we're trying to somehow characterize the churning rate, you see that by the end of the fully developed phase of the fire, so 20, 30, and 40 minutes, the values drops to 0. when you have pure natural cooling at the surface. If you take the same problem, you start looking at different isotherms, you see that the isotherms, they would possibly penetrate a bit over the first few minutes after the fully developed phase of the fire, the 50 kilowatts, but then it plateaus again. So what we saw here is that mainly wood, of course, has a specific inertia, it needs some time to adapt when it's heated, but then as soon as you remove a heat flux at the surface, then temperature distributes, and in terms of 250, 150 degrees, you don't have a much increase because wood is trying to naturally cool during the phase itself. If you look at, for example, penetration speed, which is a same concept, so the derivative of this curve, you see that actually the values compared to these ones and the 150 and 200 are still comparable. So we discuss about 1 millimeter per minute in the different phases. Then what we did the same problem, but then we start having a fixed heating phase, so 20 minutes, 50 kilowatts, and then we start having different fire decays. So here you see the case of 10 minutes fire decay, 20 minutes fire decay, 30 minutes fire decay, and 40 minutes fire decay. You see here on the legend. So 20 is the first number, and then 0 means no fire decay, and then you have like an increase of duration of fire decay, but again, the value was going from the value that applied on the heating phase, 50 to 0. What you see is that at the end of the heating phase, of course, you create more or less the same conditions with some reproducibility related to timber. But then if you start having a longer fire decay, also, in this case, the 300 degrees isotherm also penetrating deeper. Because still, again, you have still a significant heat flux at the surface of the timber that led timber also to char deeper in time. If you take the same concept for other isotherm, 250, 150 degrees, what you see again, you have a deeper penetration because, of course, lower temperature, the penetrates deeper, but you have the same concept. Wood, the heat conduction, heat penetrates during the fire decay as soon as there is a quite significant heat flux applied at the surface. What we're discussing now, we are doing through the data analysis. What is a significant heat flux for wood penetration? We can discuss about that. But this is the first study that we did. We tried to study this problem for a more comprehensive way to try to study a one-dimensional heat transfer. Because what we saw is that, the whole problem, it becomes quite complex because you have wood that chars at the surface, you have a surface regression, and then you have to start thinking about the actually pyrolysis front, the pyrolysis zone penetrates within the wood. And you can imagine as what we have been looking is this conductive term, so how the temperature penetrates in wood, but this is a quite complex problem that we didn't discuss about density, we didn't discuss about moisture content, we didn't discuss about moisture migration. We tried to solve the problem as a first study, but then I'm going to try also with different collaborators to study this in a deeper way. Last aspect I wanted to mention is that I wanted to connect also the conference. So we've been seeing a lot of these mass timber buildings for future vertical cities, discuss a lot about mass timber and possibly a lot of wood implemented in a structure. And what I wanted to highlight the difference between designing two compartments is this. What you see here, you have a timber structure with most of the compartment is not combustible, apart from the movable fuel load, while on the right you see a compartment with a lot of exposed wood. What is important for structural fire design? If you take, for example, the typical structural fire design, so you have a fire model, heat transfer model, structural model, you typically assume, traditionally, that you start from the fire model, we look at the fire exposure, we take the heat transfer model, we look at the gradients, and in the end, we do our load-bearing capacity. So this means that we can clearly decouple the problem, taking the fire, which is the effect of the structure, and applied on structures like that, because what you see, wood can burn within the compartment, but the main heat flux would actually come from what actually is burning within the compartment. Now, instead, if you're trying to design this, then we start having a bunch of things that start having an effect on the fire development within the compartment itself. So related to the movable fuel load, what is the ventilation? If you discuss about the compartment geometry, would have an effect. We would have an effect also in exposed timber. So how much wood, in which configuration, lamelle, adhesive. So this is start, and if you have encapsulated timber, would bet that timber has somehow get involved in the fire. But in general, skipping here, in general, what I wanted to mention is that when you start having possibly a lot of wood exposed, you may start to end up in a coupled problem of fire and structure itself. Because now you cannot have anymore this one directional study. And why I wanted to mention this, because fire decay and cooling is highly dependent on how the fire would evolve. Because timber, if you have a lot of timber, you would have possibly a lot of woods, a lot of fuel. So you have to make sure that, first of all, you can define appropriate fire scenario that would let you to do an appropriate structure of engineering analysis for your element. To conclude, I wanted to mention today that what you see is that fire decay and cooling phase matter, particularly for timber structure, and I hope today I explained to you why matters and how possibly would matter. Effective char depth, so the area of wood that is affected by the fire, so the char wood and heated timber, actually peaks quite late, and low temperature are actually very relevant for these values. End of fire decay, end of cooling phase, this is something that we're still researching about. If you look at the fire, the numerical study, the fire severity is not always related to peak temperature, but what we've seen is that since we are studying a transient problem, there is a direct effect on the fire duration, and this is the most important aspect. Performance-based design should include the entire fire event, so all phases, and I'll show you, and hopefully I'll convince you why you should look also in fire decay and cooling. And then I wanted to finish with a positive message that timber buildings can be perfectly done if they're done right. I'm not here to say we should completely remove this, we should move in a different direction. But if we think carefully about this problem, we have all the information today that possibly we can solve some of these problems. And if the problems are too complex, like a complex exposed timber building with a lot of exposed wood, we should define a quite robust way of defining or designing the timber, because we are actually playing with fire. We could end up in a very dangerous situation. Because if you look at, this is a reproduction of the Great Fire of London on 1666. What is important is that what we see in the timber industry, and we're here today, I believe I don't have to convince you about why timber is important, why we should build more with timber nowadays. But it's very important. We are fighting big lobbies in the construction environment. And when wood was implemented a lot in the cities in the past, and at a certain point we started implementing fire safety requirements and started moving wood from cities because it was getting very dangerous. And many cities burned completely from top to down in different years. So it's very important to make sure that mainly we don't screw it up too much, because if in case anything goes bad or we get any bad publicity related to this topic, and fire is always, you've seen also in the conference, is always a big topic, they're gonna start removing wood as a way to solve climate emergency. And this is very important to us. So, and the only way forward I see, we should have, today we are fire engineers and researchers, but we should have a close collaboration discussion among all the decision makers in this topic. So from manufacturer, fire rescue service, architecture, regulatory bodies, because it's very important to look into this in detail. Finally, I would like to acknowledge my research team at ZAG and Frisbee. I would like to thank Josh and David for putting this together and inviting me today, my research collaborators. I also put here the main references I've been discussing today regarding to books, handbooks, and standards, various scientific papers where I took what I discussed, but also taken pictures, plots, and videos from other researchers. And finally, I would like to invite you to a conference that we are arranging in September in Ljubljana, in Slovenia. That is going to be from the 3rd to the 5th of September. Most of the peer review process and poster submissions is already closed, but I just wanted to tell you today that at the beginning of September, if you want to come to Slovenia, we have the 5th European Symposium on Fire Safety Science. Finally, thank you very much for being here to listen to me, and I will be happy to take any questions.
Thank you very much, Andrea. We do have questions both in the room and in person. I will just remind everyone, I will be posting this video on YouTube hopefully today or very soon afterwards. So you will be able to go back and re-watch this because I know I probably will need to as well. You've already got a couple of questions in the chat, and then we might get to some in-person questions so I can end the Zoom for you. If that's all right.
Yeah. You have the timing.
You just go into the chat.
Pointer.
That's at the top, the chat box.
Where is it?
Where's got
Chat. Okay.
You've got a couple of comments in there.
Which one should I start from this or from the bottom?
From the top.
Okay, you have focused on natural cooling for structural elements. Can you speculate on the effects of firefighting intervention, thermal shock from cooling the timber surface more quickly? Yeah, I mean, this is a very fair point. This is something we've been discussing I've been thinking myself because I started from somewhere discussing about the problem, and what we did now, we have been looking at natural cooling. So when the fire dies, we have natural cooling. Of course, could have an effect on firefighting intervention. What I can imagine is that from the structural point of view, if you cool the sample, if you cool the elements, and if you cool the materials, you would possibly regain mechanical properties if you cool it down. Regarding how much this may affect, I'm not 100% sure. What I can think for sure is possibly post-fire effects of having a lot of the timber structure, a lot of timber elements that would be completely watered down after the fire event. That would goes into a discussion of durability and resilience of timber structure, not only during the fire, but also what happens after the fire. Danilo, this is important. Yes, Josh? Okay. You mentioned size of timber matters for columns. Is there a minimum size that is okay for a compartment fire? This is mainly related to, the fire conditions. So we're discussing about a column which has a size, has a specific mass, a specific thickness. I discussed today about, for example, the importance of fire duration and the column size, apart from the char layer and the collection possibly of heat in the core of the column itself, depends on the fire conditions and also the load of the column itself. So depending on compartment, possible appropriate fire condition you would experience, of course, the column size matter, but the column size also matters depending on the conditions they would experience in the compartment itself. Great presentation. Thank you, Romara, very much. Thank you very much. Is the timber strength recoverable below a certain temperature? Oh, this is a very good question because what I used, and I show in the slides, I used the reduction of mechanical properties according to Eurocode 5 that, if you go into the literature, is a sort of envelope conservative quantification of the mechanical properties at elevated temperature. So since Eurocode 5 is a design code, what they've been doing in order to characterize the mechanical properties at elevated temperature, they've been trying to be extremely conservative in characterize these properties because it's a design code. So people use it to design and we want to be conservative and safe. What I've seen in research is, first of all, that if you look at timber at elevated temperature, first of all, up to 100 degrees, you sometimes have even a gain, a strength and stiffness gain in timber, because actually by drying the timber, you're actually getting strength. Then if you discuss about residual mechanical properties, what had been shown, there is a paper that has been recently published in Construction and Building Materials that I can link, but also some papers that have been presented over the last few conference days. People are discussing that mechanical properties of timber would be possibly recoverable below pyrolysis temperature. So we discussed about, we've seen 180, 200 degrees, but as soon as you have a significant thermal decomposition, would be possibly also related to timber species, then possibly will be recoverable. But in this study, particularly the numerical one, I assume non-recoverable. So the mechanical properties would be associated by the maximum temperature experienced by the specific piece of timber. Okay, this is Josh. And to learn more about timber buildings in coastal regions. Yeah, I think this is a bit outside of my presentation today. Thank you for your presentation. Do you think that increasing the number of unknown parameters, such as moisture content, thermal inertia, and so on, makes the problem more complex and hinders the broader application of timber structures? So first of all, I mean, the immediate answer is yes, but also the median answer is also yes, the problem is complex. It's not, we are making the problem complex, the problem is complex by itself, because you have a lot of aspects. What I've been discussing, for example, and we have been experiencing, I haven't had the time to present it today, but for example, in the numerical model, I assume wood as a solid element. Wood, nowadays, that we work with laminated, glued timber structures, is a composite that behaves possibly as solid, but not always. We can discuss about char fall-off, we can discuss about the lamination. So one of the approach that, for example, I show you in the numerical model today, the concept was to try, since the problem is complex, I didn't want to focus on the solid aspects, so density, moisture content, all of these timber species. I said, okay, if the fire condition drives the problem, and we are not 100% sure about the fire problem itself, let's parameterize it and see what actually matters the most. And what I show you today, from the specific study with their assumption, its assumption itself, I showed that you can be specific about maximum temperature, but what matters is what somehow the duration of fluid of fire or a fire that would lead to an important heat flux to the structural element.
If you have any questions in the room, just speak loudly so the microphone can pick it up.
Or you can also come here and ask the question here if you want.
I will become start.
Who should start? Luis, please come. You can.
Thank you. It's just I have way too many questions, and thank you for a very nice presentation. I think your point is that everything we have done in the safety fire safety research is wrong, basically, and we are oversimplifying the problem, and we are not taking into account a conservative scenario, which would be taking into account the cooling phase, right? This is more or less the message you are trying to convey here.
Yeah, but it's also very important to think that the cooling phase matters, but is highly connected to what actually happens during the heating phase, fluid development phase of the fire, because it's still the most challenging situation for a structure. And for example, if we discuss about durations, if we somehow we define the duration on the fluid development phase and we take that duration in a very conservative way, then possibly we can cover the effect of the cooling phase. But then this goes into the whole, what I showed today is that, yeah, we can discuss about timber and everything, but what you see, fire, since we are doing structural fire engineering, defines the problem and defines also the challenges related to that. And what I showed is that the definition of the fire scenario has the biggest effect compared to some aspect that would have a secondary effect compared, for example, timber density, moisture content, and all of this. So everything, the level of safety is directly related to how you define the fire scenario and the possible characteristic fire they would have in your compartment.
So we need to increase the safety factors.
Yeah, but what is the safety factor they're using nowadays in our design?
I'm not a fire safety engineer, so which makes me leads me to the next comment, which is transient or time is a very important thing to take into consideration. Fire severity was measured at the beginning of research as temperature, and then somebody realized, well, if I'm boiling water, I'm giving energy to my system, and the temperature is constant. So we have all these processes where temperature is not a good parameter. So let's have a look at the energy. And then somebody says, but if we have different systems, we need to normalize that. So they divide that by time and area, and you have the heat release rate. And now you're saying that time is an important factor, of course, because your timber is receiving more calories if it's more time there. So it's a matter of energy. It's not, for me as a chemist, it's more energy, it's not time. And the processes, of course, they will degrade more the timber if it receives more calories than another piece of timber. So I don't see much like the transient thing for me. It's more like energy.
Yeah, but why I connected to that is that because at least I saw that was the most important aspect of related to duration is the fact that, the main concept related to other materials is that wood also combusts at its surface. That of course combustion depends on density, oxygen concentration, all of these things. But then what happens is, or at least I want to look into this more in detail, but it could be that if you are within a certain range of heat flux on applied on the timber surface, what actually matters, it doesn't mean if it's 40, 50, or 60 kilowatts, but matters again, the duration itself. Because in the end, it's a significant heat flux that is paralyzing and affecting the timber, but then what I would focus is more on the duration, because in the end, the energy balance, the energy comes from the surface. And even if the heat flux is low, but timber is still burning and you have flaming combustion on the surface, the heat and salt also comes from its flaming itself. And of course, it's a loop process because the more flaming, the more pyrolysis and all of that.
Okay, well, it's something we can discuss more, but
Definitely.
I will leave the opportunity to other people to. We have a chicken there.
Yeah. Thank you, Luis. Yeah, I come, Julian. Yeah.
So thank you, Andrea, for that amazing and really comprehensive presentation. I saw you did both numerical and experimental studies, which I know you imposed different boundary conditions in each. One was the temperature from the Eurocode curves. The other one was governed by heat fluxes. Did you have the chance to compare the two of them in sense of the in-depth temperature profiles and maybe see some relative differences that could be attributed to phenomena that you mentioned, like moisture migration or some other things, or could you attribute it more to the geometry of the specimen that you were testing, or what kind of things? I know it's like
No, I mean,
but
you're actually raising a very important point that I haven't had the chance yet to compare, because this study, the experimental study was finished in May. So it's really new, and I just wanted to present today because what I realized that we can always keep everything in this numerical and modeling ideal world, but then where actually you go into testing, then you see another bunch of problems. And the first feedback I can give it to you is that the biggest challenge I found is that wood doesn't behave as a solid. Apart from the intrinsic repetitions between we haven't managed to get two tests look the same. So we start putting, envelopes. That's why, you don't see all the tests in the slides I presented, but there was a lot of tests and we got trends. And, but then the biggest challenge we start having, for example, during the cooling part of the fire decay part, we also had the challenge also related to char fall off. One of the questions I haven't explained, why we focus on the 20 minutes heating phase. Because based on the lamella we had, if we would push more, the fully developed phase of the fire would end up having problems with char fall off and delamination, which is scale dependent. And I had this sample of this size, I have a radiant panel of this size, so I couldn't solve all of that. So it's more complex than what it is. And if any of you in this room online would like to join me and study this problem, please feel free to reach me. And look at Ian. Ian is looking at moisture migration only and spent the last 2 years struggling how to measure, how to control that. And it's a very small problem within the big one. So, yeah.
thank you.
Trying to build on it, but still far away.
Yeah.
Right.
Thank you.
Thank you, Julian. Ian?
Yeah, thanks, Andrea, for a fantastic presentation, as usual. I have a lot of questions. I'm going to try and keep it to two in the interest of time. My first question was, when you've done your structural analysis based on this calculated zero strength layer, and I know you used I think the reduced properties for both strength and stiffness, was it?
No, there was in the strength ratio, in the strength domain.
Okay.
So it was because if you think about a timber wall, then I was looking at area and then I was multiplying the strength times the area. So it would be an element in full tension or full compression.
Okay.
So I didn't, because otherwise you have to look at the stresses distribution,
Yes.
which depends on the lamella thickness and duration.
Yeah.
Kept it in a pure strength domain.
Okay, so that definitely partly answers my question, but then I'll just ask you to comment on, I mean, what we've seen in some recent papers is that for compression elements and CLT walls and CLT glulam columns in compression, what actually ends up dominating failure tends to be stiffness related, and especially that you often have during the cooling phase some induced eccentricity in the loading, which then ends up with runaway buckling failures. How do you think, or I mean, do you think that that can be addressed through the zero strength layer, or what are your thoughts on sort of buckling failures in timber compression elements?
I mean, that connects to the previous concept of timber section and column section, because again, so buckling is a stiffness problem, but also depends on the height of the column itself. So then, you have to have a project. You can always study it numerically as a theory itself, but the buckling problem is element specific problem.
Mm-hmm.
So you have to start looking possibly at projects. Projects, connects again to fire condition you would experience. Then if you ask me about, the possible eccentricity provided by the fact that you would have a side which is more heated, where the penetration would go deeper, and then you would have some eccentricity, so you have some moments within the column itself. I don't think anybody does it, but you would have the same problem in a concrete column, because you have you would have, or a concrete wall. But what we do is, even if I think fire tests, we do an eccentric load, we test a wall, then you have an eccentricity given by the fact that heat affects one side. But I found it, I mean, you have to go very deep and very advanced to start thinking about these problems, because it's an element problem, an element related problem.
Yeah.
But definitely related to stiffness as well.
Yeah. Okay, thanks. Another question that I had related to your experimental study, and you were showing that at some point during the cooling phase, or beginning of the cooling phase, more or less, the char layer, or it was at the end of the cooling phase, basically the char layer has stopped moving. And then you also go down to 150-degree isotherm, which basically stops moving as soon as you exit the cooling phase, or the decay phase, sorry. And I definitely agree with that, and that's something that I've seen as well. But I was just wondering, I mean, I think what happens is that temperatures above 100 degrees, those isotherms tend to stop very rapidly as soon as you no longer have a net external heat flux. Because obviously at 100 degrees, you have this very strong endothermic moisture term. I was wondering, did you measure isotherms below, or did you analyze isotherms below 100 degrees? And for example, the 80-degree or 60-degree isotherm, whatever it would be, how much further that continued to penetrate during the cooling phase? Because I could imagine when you don't have such an endothermic effect below those temperatures, that those isotherms might still continue to move for quite a long period of time. So yeah.
That's a very good point. Again, the short answer is that so this was part of a master thesis that was a specific time to carry out this experimental campaign. And you've seen the tests where 20 minutes, I mean, the tests I presented today were 20 minutes heating phase and up to 40 minutes cooling phase. So it was 1 hour of fire test. And then we ran tests up to 4, 5, 6 hours. Temperature never dropped below 100.
Yeah.
So if we wanted to look into that temperature, we could have done one test every 2 days.
Yeah.
Because the whole penetration of that isotherms takes very, very long time.
Yeah.
Which is also a bit scary, because that is why possibly in the test I show you the column in the furnace, I would have failed 2 hours after the end of the test, because these low temperatures matters and keep penetrating in a very long duration. So you would need to do tests of 1 test per day.
Yeah.
And log that data for 12 hours.
And especially when you have stiffness reduction at such low temperatures as well for compression elements.
Yeah.
Yeah.
And the elements were not loaded. I was
Yeah.
just looking on the thermal side. Yeah, I mean, you know, you're an experimentalist as well. You can explode the matrix quite easily, and yeah.
Okay, I'll leave it at that. But yeah, fantastic presentation.
Yeah, we
Thank
can
you
also
so much.
discuss later.
Yes.
Thank you again.
I think there was another one online.
Okay. Does a heat transfer analysis based on estimated fire compartment temperature and the thermal properties of timber is considered good enough to estimate the capacity of a timber element during a fire without considering the impact of charring in the heat transfer? So I believe consider the impact of charring in the heat transfer, you possibly refer to surface regression, oxidation of, and all these aspects. So the change in the geometry itself. So so I have all my doubts about, you know, these effective thermal properties of woods, which were designed and they were defined mainly on implicit and regression analysis based on furnace test under standard fine conditions. So they come all the limitations, but what I always tell students is that if you look at the specific thermal properties of wood at elevated temperature, you start seeing, for example, in the specific thermal conductivity, a huge increase after 400 degrees, which is mainly related to the fact that in order to consider a fixed geometry of the elements, somehow you have to take into account to possibly char fall off and surface regression. And in the way that is done, according to, for example, Eurocode and effective properties, you mainly increase a lot thermal conductivity that goes above 2 watt a meter Kelvin, that somehow implicitly takes into account the fact that you have surface regression. And this is the way that by simply changing three properties, so specific heat, thermal conductivity, and density, you actually can solve this problem without changing the actual geometrical dimensions of the elements. Arwa, please. Yeah. I mean, I do. I don't know about people online. I don't know. Okay, so I'll be around also the rest of the day, so we can also always discuss.
All right, thank you. This will be a very short question. I guess, like, if I were an architect sitting in this meeting, based on your results, would you advise me to, like, just not expose columns and beams? Like, it's okay to expose walls, but beams or columns are not okay to expose, because if they char, then they char all around, and then it's insulated all around, and then there's no room for heat dissipation. And even if you could regain any strength in the timber upon cooling, you just won't be able to regain it because you can't even cool down the column. That's the question.
I mean, thank you very much for your question. The first point is that columns in the modern structural systems, also in earthquake engineering, we usually design strong columns and weak beams. So columns are a very important element in the structural system, particularly when you have frames. So this is, you have to make sure that you design them in a robust way, that you don't have major loss of columns in a fire event. So that's why it's very, very important. So the first short answer, architect, try to have a conversation with the fire engineer and see at what extent a different amount of exposed wood would have an effect on the consideration of the fire conditions in the compartment that you're designing. Then if you have a timber frame, which is possibly exposed columns and beams, I would say if you have a proper analysis, if you input a different level of robustness and related also to uncertainties, I would say, yes, you can leave them exposed unless you do your analysis properly. As a structural engineer or fire engineer, you are confident with your results. And you don't oversimplify and ignore many of these problems.
If I could expose a surface, better to expose the walls than to expose columns? Like, is it less risky to just expose the walls and cover the columns?
This size, I mean, what I know ceilings is usually more accepted to be exposed than walls. Because regarding between columns and walls, is a load bearing wall as well, possibly. So I wouldn't answer that. I would look at the project and look at that in detail, because
Just on the wall, you can have a bigger area of pure load bearing.
yeah,
So it becomes then fire safety issue more than structural.
is again, as Ian or previous questions, is you have to take the project, because you cannot just simplify and say, is some of the codes, this is some of the also the aspects we have seen in the conference a bit scary, that people start prescribing a maximum surface area in a compartment, say you can expose up to 30%. But then as a fire safety engineer, you immediately know that if you expose columns or if you expose a ceiling and a wall next to each other, you could have started having this re-radiation and possibly never extinguish the fire. So it's not just a matter of, it's not so simple. That's my main answer. So I guess that's over. Stavros? Okay, so maybe we can release people online.
Yeah.
And
I might just wrap it up there for online. I'd like to thank Andrea for his time,
I able
attention,
to have a last slide.
care.
See you in Slovenia.
See you.
Wanna come over?
Thank you to everyone online who's joined us for this presentation. We also have Jose Terrero in 6 days' time presenting fire behavior of mass timber compartments. So yeah, thank you for your time and see you next week, hopefully.
Thank you, everyone.